In the previous lesson, we measured the relationship between GDP growth and its immediately preceding value. That was the lag 1 autocorrelation. But economic variables may also be related to observations from 2, 3, or more periods earlier. Today, we extend our analysis to higher-order autocorrelations and introduce the Correlogram. Let us continue with our simulated GDP growth rate for an assumed economy. We generate a persistent series in which current GDP growth depends partly on its previous value. The series shows gradual movements rather than completely random jumps. This persistence suggests that GDP growth may be correlated not only with the previous year, but also with observations further in the past. Lag 1 compares an observation with the value 1 period earlier. Lag 2 compares it with the value 2 periods earlier. Lag 3 compares it with the value 3 periods earlier. The same idea continues for higher order lags. As the lag increases, we compare observations that are progressively farther apart. For a persistent series, the relationship may remain positive for several lags, although it generally becomes weaker as the lag increases. We can now calculate the sample autocorrelation for each lag. For lag 1, we compare xt with xt minus 1. For lag 2, we compare xt with xt minus 2. For lag 3, we compare xt with xt minus 3. And so on. For lag s, the sample autocorrelation compares observations s periods apart. The numerator measures how these observations move together through their deviations from the mean, while the denominator measures the total variation in the series. Here, x bar is the sample mean. The resulting value is the sample autocorrelation at lag s. Here, we define a general function for calculating sample autocorrelation. The function takes the data and the chosen lag s as inputs. It first calculates the sample mean, then forms the lag deviation products and divides their sum by the total variation of the series. This allows us to calculate the autocorrelation at any lag simply by changing s. When s equals 1, we obtain the lag 1 autocorrelation, which is 0.74. When s equals 2, the autocorrelation falls to 0.542. At lag 3, it falls further to 0.392. We can then repeat the calculation for higher order lags.
Instead of calculating each lag separately, we can calculate the autocorrelations for many lags at once. This table shows how the strength of the relationship changes as we move farther into the past. For a persistent series, autocorrelations often decline as the lag increases. For our simulated GDP growth series, the autocorrelations gradually decline as the lag increases. The values are positive for the first several lags and become smaller as observations are separated further in time. By lag 8, the autocorrelation is close to 0. And at the 9th and 10th lags it becomes slightly negative. This pattern suggests that the strongest relationship is with recent observations, while the relationship becomes weaker as we move further into the past. We now have a sequence of autocorrelations across different lags. This sequence is what we will visualize in the Correlogram. A convenient way to display this sequence is called a Correlogram. A correlogram plots the sample autocorrelation against the lag. The horizontal axis shows the lag. The vertical axis shows the corresponding autocorrelation. Each point represents the sample autocorrelation at a particular lag. The first point is the lag 1 autocorrelation, R1 equals 0.74. The second is R2 equals 0.542, and the third is R3 equals 0.392. The autocorrelation then continues to decline, 0.276 at lag 4, 0.187 at lag 5, and 0.117 at lag 6. By lag 7, it has fallen to 0.063, and by lag 8 it is almost 0, at 0.020. At lag 9 and lag 10, the values become slightly negative, at minus 0.015 and minus 0.044. The overall pattern is therefore one of strong positive autocorrelation at short lags, followed by a gradual decline towards zero. This gradual decline suggests that GDP growth exhibits persistence, but that the influence of past observations becomes weaker as we move further into the past. The correlogram becomes even more useful when we add approximate significance bounds. Under the null hypothesis that the population autocorrelation is zero, the approximate standard error of a sample autocorrelation is equal to 1 divided by square root of the number of observations in the sample. Using the 5% critical value of 1.96, the approximate significance bounds are plus and minus 0.358. We can now compare each autocorrelation with these bounds.
The dashed lines at approximately plus and minus 0.358 represent the 5% significance bounds. The first three autocorrelations are 0.740, 0.542, and 0.392. All three are above the upper bound of 0.358, so they are significantly different from 0 at approximately the 5% level. At lag 4, the autocorrelation falls to 0.276, which is inside the significance bounds. The remaining autocorrelations are also within the bounds. Therefore, in this simulated example, the evidence for statistically significant positive serial correlation is strongest at lags 1 through 3. The later autocorrelations are smaller and do not provide sufficient evidence of a non-zero population autocorrelation at the 5% level. The shape of a correlogram provides important information about the underlying time series. In our example, the autocorrelation starts relatively high at 0.740, falls to 0.542 and 0.392, and then gradually approaches 0. This gradual decline is characteristic of a persistent time series. A correlogram with values close to 0 across most lags would suggest little serial dependence. An alternating sequence of positive and negative spikes could indicate an oscillating pattern in the series. Thus, the shape of the correlogram gives us a compact visual summary of how dependence changes as the lag increases.